actually 10216, was that just a few years ago now, ALMA detected methyl cyanide emission. So methyl cyanide is a very common interstellar molecule. It's used as a temperature probe of many interstellar regions. And it was expected that any methyl cyanide that was detected would be detected in the outer shells. It would be driven by some sort of photochemistry. You break up some simple molecules and then rearrange into methyl cyanide. Instead, what ALMA saw was that there's a ring of methyl cyanide emission at 2 arc seconds from the star, and it contains a hole that's about 1 arc second in size. And so when you look at so this again is an observation by Chernacharl. So when you look at their kind of standard models and their clumpy models, so this is the solid line again is just the kind of standard with a 1 over r squared distribution in density and an external interstellar radiation field. And you see the peak occurs far out in the star a few times 10 to the 16 centimeters. When you let sorry, this so this is the observational fit. This is the standard model fit. So densities peaks at about 10 to the 410 to the 16 or so. When you look at their clumpy model, when you let photons get in, then in fact they find that a couple of arc seconds, which is about here, they're a factor of 100 too low in abundance, but they also predict lots of methyl cyanide inside 1 arc second, which isn't seen in these models. And so, in common with many people who study astrochemistry, if you don't know what's happening, you set screens, and so the process is happening on dust grains. So the last refuge of the scoundrel, it's sometimes called when you do this. So there's still an uncertainty about how this molecule is formed. We decided a couple of years ago, to look at these clumpy models, but to do it in a different way. So rather than make an assumption a priori that a couple of % of interstellar photons got right into the inner envelope, we decided to make a model where we distributed clumps of dense gas within the outflow. And so we used 2 parameters. One was to measure interclump density through a parameter FIC, which is the ratio of the interclump density to the smooth density that, if you like, that you would have in a 1 over r squared flow. And then to put a certain volume of the envelope into the clumps defined by F volume. So we split our envelope, if you like, into an interclump medium and a clump medium. And we worked out, instead of assuming a few % of photons we're getting through, we worked out, if you like, an effective optical depth that an interstellar photon from external would see as it flows into the envelope. So the solid line here is the 1 over r squared flow. So typically, this is for a mass loss rate of about 10 to the minus 5 solar masses per year. So this is the visual extinction. And as you go from the interstellar medium, it's just a 1 over r plot. So you get about 100 magnitudes of visual extinction at 10 to the 14 centimeters. So the envelopes here are really opaque to ultraviolet radiation, which might be 5 times higher or something than this 100 magnitudes. But if you let the medium be clumpy, then in fact, it depends also on the clump size that you have, but you can reduce the ultraviolet, or the visual extinction, and therefore the ultraviolet extinction quite dramatically in these flows. And this is just the exponential extinction that a photon would see as you go from 1 over r squared flow to a much more clumpy flow. So you can get perhaps only a reduction in the photon flux by about 10%, again to a few %, depending on the physical conditions you put in the clumps. So we looked at, again, just trying to think this was perhaps a little bit more an interesting way to do it, and again, this is quite a complex.
A spherical clue?
Yeah, so we assume it's spherical.
And then this H is the diameter, or what is this H?
Oh, H, sorry, I should say. H is the kind of mean free path we have between the clumps. So so it tells you how far the photons can travel. So the clumps also, we set them up with an initial size distribution, but they also expand as they go through the
Then that makes sense that when they are closer, you reduce
you reduce
because otherwise you expect vice versa.
Yeah.
What are clumps of gases?
Yeah, these are just, but we're assuming actually that both the gas and the dust go together. We're assuming that both the gas and the dust go together. So the clumps have greater extinction, a greater density, but also greater extinction than the interclump.
What confines the pressure, external pressure? Is it pressure confined?
No, these are just expanding into the vacuum, so it's
Well,
just
they don't exist after the dynamical time.
yeah, but so the expansion time
After
scale
sound crossing time, they would not exist if there is nothing confining them.
okay.
Sound crossing
No,
time is
so
very short.
there's okay, sorry, I said, but there's the material in the envelope itself, which is
So external
so-
pressure
so the-
confines.
so the material is expanding adiabatically, so it's coming out with a set of densities and temperatures and pressures.
Right,
and everything.
So that's not my question.
so-
The question is, we look
so-
at the clump,
It's sitting,
it's sitting in an external pressure, and that's what keeps it.
yeah, the interclump.
Now that means that you don't have freedom in the pressure of the ambient medium surrounding it. It's not as if you can say the clump is something, and I don't care, there is vacuum outside. You have to consider the medium outside that confines it, which provides some opacity.
Yeah.
And how much is that opacity?
Okay, I need to look at that. Okay, so this was quite a complex diagram, but really all I wanted to show you here was the kind of solid lines. So these are for different mass loss rates. The solid lines are what you would get in the typical 1/r squared flow, and then the differences in these curves, what happens as you change the parameters of the clump size distributions, filling factors, and so on. So you can get you can get quite large differences in terms of fractional abundances of particular molecules in these inner envelopes. They don't always depends on the molecule, but they don't always translate into large differences in column density, because sometimes these big changes happen at small distances where they don't add much to the volume. But you can find in some mass loss rates quite large differences in column densities of some molecules. We tried to look at this model. So this is some unpublished work that Denise Keller has done at the VLA, which has looked at a variety of these kind of carbon chains. And so again, this is the external rings of complex molecules, and she's been able to derive. So this is red is HC3N, blue is HC5N, and able to work out. So she's taken azimuthal averages around this to work out where these rings sit, and in general, she's finding that the bigger molecules sit generally slightly outside the smaller molecules, and she's done the same for some of these other just pure hydrocarbon chains. But you see that the distributions are extremely clumpy. There are gaps sort of in the rings of this region, which has been known for a long time. The galactic plane is in this sits along here, so there may be additional radiation coming in from this direction and from other directions. But you see, although there's this kind of spherical, some sort of spherical distributions, the clumps themselves, these circular distributions are extremely clumpy. And there's other rings that are seen if you look at scattered light in sodium lines or potassium lines, for example. You see many of these kind of rings around RC 10^6 at least in the scattered light. We did try and this is another one that I guess is just a failure rather than anything else. So we did try to use our model to fit the distributions that Denise Keller got from the cyanopolynes that are on the left-hand side and the hydrocarbons that are on the right-hand side. We found that we ran about 5,000 models. We found that if we chose the models that fitted the carbon chains, and they didn't fit the cyanopolynes. So the lines are just our model lines, and the colors are where these different molecules sit with their uncertainties, where their peak emission is. And if we fit the cyanopolynes, then we didn't fit the hydrocarbons. So there's lots of work still to do, but we're still trying to figure out how to put rings and clumps all together in some model. So far I've talked about the effects of external radiation on the envelope. I want to go to talk about the possibility that there may be internal photons that are important in some of these objects. So actually Rudy Montes here has published a paper a couple of years ago where he used Galax observations to study over 300 ATB stars, and found out that in certain in broadband detections at NUV and FUV wavelengths that there were a significant number of these detected, about 10% at the shortest wavelengths, but a significant fraction at longer wavelengths. And his conclusion from that was that if you looked at the variety of correlations that one could do, if you took out the effect of reddening, you corrected for distance and so on, that you saw some anti-correlation between the flux both in the near UV and in far UV with this parameter mass loss rate over expansion velocity, which is a proxy for density, if you like, in the shell. So at higher densities, you're getting you get less flux measured than at lower density numbers. And he also showed that certainly in some cases that the NUV emission was in phase with the optical light curve. So he concluded that some of these objects do have ultraviolet radiation that you can detect from them, and that this UV radiation is intrinsic to the ATB star. It goes in phase with the pulsation, so it's intrinsic to the star. So that was a very interesting observation, and it got us to think a little bit about what would happen if instead of interstellar photons coming in, that you had also photons generated from either from the star or from perhaps a companion to the stars. I'll talk about in a minute. And so we just did a very toy model where we looked at the effect of just taking the stellar black body radiation and calculating what would happen to the chemistry in these inner envelopes. We were interested in trying to explain the methyl cyanide observations, for example,